Hi there! Welcome to Lesson 3.5, Vertex form of a quadratic function. So we just finished up the lesson where we looked at quadratic functions in standard form, and we learned how to find the axis of symmetry, the vertex, even the y-intercept, and we learned to use all those things to create a graph that represents that function. Well, this lesson has the same learning goals essentially. We're going to find the vertex and axis of symmetry of a quadratic equation or inequality, but this time we're going to find it out from vertex form. So that we're going to look at what vertex form is and how we can find those exact same things, but when the function is written in a little different form. And we're also going to learn to graph quadratic functions and inequalities in vertex form by finding the vertex and the axis of symmetry. So we're going to learn how to actually graph them, not just find them, but use them to actually graph the functions. So vertex form, that's a familiar phrase. I mean, we use that with absolute value functions. You may remember that the vertex form for absolute value functions looked like this. It was a times the absolute value of x minus h plus k, where hk was the vertex. And remember that the A told us about how skinny or wide the two branches of the absolute value graph were. In other words, like what the slope was of those. And the H and the K in vertex form told us where the vertex of the absolute value graph was. Well, remember we talked about that there's some similarities to a parabola and an absolute value graph. And so one of them is that vertex form looks almost identical to vertex form of absolute value. And here is vertex form for a quadratic. So notice really the only thing that's different here is that instead of the absolute value brackets, we have parentheses. And we also have this squared after the parentheses because this is, after all, a quadratic function. But essentially it works really in much the same way that vertex form worked for absolute value. Now for quadratic in vertex form, the vertex is the coordinate h comma k. And again, that the h is the thing that's being subtracted from x, and the k is the thing that's being added on the end. That's the actual vertical slide amount. Now we talked about the axis of symmetry in the last lesson, and we said that that was the line that cut right through the parabola so that each of the branches was a reflection of each other. And we said that it was the equation was x equals whatever the x coordinate of the vertex was. It was x equaled the opposite of x equals the opposite of b over 2a, and it turned out that that was the x coordinate of the vertex. And so, but in this case, we can tell the x coordinate of the vertex instead of using a formula. We can just look at what is being subtracted from h, or really, in other words, what makes this parenthesis part, this x minus h, equal to 0. And so x is going to be equal to h. That's the x coordinate of the vertex. Now, much like the how steep the branches were on the absolute value graph, we could tell by the a that's out in front, this thing right here. Well, we can use that same piece of information to determine the width and also the direction of the parabola, because the direction will be, it'll face down if it's negative. So if we have one of those sad face parabolas, that's when the a is negative. And when the parabola opens up, we'd have a positive a. Now, although the standard form had a lot to offer us when we looked at in the last lesson, what we like about vertex form is that it shows the transformation on a quadratic equation in respect to its parent graph, which is f of x equals x squared. So it essentially tells us how the parent graph is moved from its original position at the origin to its new position, and whether it's made wider or skinnier. In other words, if it's stretched or compressed, and also if it's reflected over the x-axis or the y-axis. So really one of the first skills we're going to look at is something we've already done with absolute value graphs, and that's looking at a function that has been transformed in some way and see if we can describe the transformation by comparing the equation back to the original parent function x squared. So let's go ahead and take a look at these examples. So number 1 is f of x is equal to x squared plus 9. So if we compare that to vertex form, we can see the only thing that's been done is they've added a 9 on the end. And we know that from back when we studied the absolute value graph that means that's going to be a slide up 9. And it's using this rule for transformations, f of x plus k. So we're just taking the function and adding k on the end, so it's sliding it up 9. Whereas in number 2, they're using the rule, transformation rule, f of x minus k. They're subtracting 2 off the end, so that's a slide down 2. What about number 3? So again, comparing it back to x squared, which is our parent function. So you can see that inside the parentheses here, so they went in and took x and they replaced it with x plus 5. And since we know that x lies to us, we know that this is a slide in the opposite direction that we might think. We might think it's 5 to the right, but this is a slide 5 left. And the negative out in front, of course, gives us a reflection over the x-axis. So reflect over the x-axis. So that's what that negative does, is does the reflection over the x-axis and the plus 5 to the x. And again, it's being done directly to the x, and that's why it's grouped in with x in parentheses. And then we have the squared on the outside. So you can for sure see they took out the x here, and they replaced it with x plus 5, which is a slide 5 left. Let's go ahead and do number 5, and we'll leave 4 and 6 for you try questions. So on number 5, there's what's been changed here is there's a 1/3 being multiplied by the x squared. And remember that multiplying by a value that is between 0 and 1 causes a vertical compression. So this is going to be a vertical compression of factor 1/3. And the plus 2 off the end is applying that rule, f of x plus k. So in other words, this is going to be a slide up 2. So let's go ahead and pause now, and we will set 4 and 6 to be you try questions, and just asked to, again, describe the transformation that's going on and comparing it back to the parent function. So go ahead and pause the video now and complete 4 and 6 as you try questions. Well, thank you for giving those two a try. Take a second to check your answers, and be sure to make a note if you have any questions. Okay, let's go ahead and take a look at number 7. So Mason graphed the parent function of a quadratic equation. Then he reflected the parabola over the x-axis. So he reflected over the x-axis. He translated it 7 units up and 3 units to the right. What is the equation for the new parabola? Well, so first of all, the reflection of the x-axis. So we know we can reflect over the x-axis by simply putting a negative out in front. That's going to have the effect of taking it and making a sad face parabola. Now, the reflection 3 units to the right. So we've done the reflection of the x-axis. Now the reflection, the slide 3 units to the right. So we know that anything that's going to go left or right is going to directly affect x. So we actually want to go right in here and replace x with x minus the slide amount. So in this case, we're going 3 units right, so that would be replaced with x minus 3. And then don't forget that squared off the end, because this ultimately is still a quadratic, and we were taking x squared and we're replacing it. And so when we replace x with x plus 3, that is the new quantity then to be squared. Now finally, so we've got 2 of these transformations completed. Now the final one is the translate it 7 units up, and so we're going to apply the rule. We just add the 7 on the end, and that's going to have the effect to slide upward. And this is our final function that does those 3 transformations. So it's time to move on, and let's actually try at graphing some of these quadratics in vertex form. Let's turn the page. So the first thing we did when we graphed quadratics in standard form was we found the axis of symmetry. Well, the axis of symmetry is really easy to find in vertex form. That's actually a very handy part about this form. is all you have to do is locate whatever the slide left or right is, and that'll tell you where your axis of symmetry has moved from the y-axis to where it's moved to. So this x minus 2 here, this slide left or right, that actually is a slide 2 units to the right, and what that's doing is moving the axis of symmetry over to x equals 2. And when we did this with standard form, we then would have to take that 2, substitute it into the function, and find out the y-coordinate of the vertex. But we can actually read the entire coordinate of the vertex right from the equation. It's just the horizontal slide amount and the vertical slide amount. And so we can see that this is horizontally slid 2 units to the right, which is 2, and it slid 3 up. And so that's going to put the vertex at 2, 3. So if we were to go ahead and sketch these things on our graph, our axis of symmetry at 2 would be right here. Of course, the vertex is on that line of symmetry. It's actually on that line of symmetry at 2, 3. So that would be right here. This is going to be a parabola that opens up. So we do have some of the key things, but we need more points now. Now, one way we talked about graphing these was to put that vertex in the middle of your table and then pick points on either side of it. And that's one way we could do that. Now, another thing we did is we talked about taking and finding the y-intercept. Well, you can't really find the y-intercept unless you have it in standard form. So the way that we would have to do that, if that was what we chose to do, was we would have to take this and expand it out by, so what x minus 2 squared really means is x minus 2 times x minus 2, and then we have the 3 off the end. So we would go ahead and have to FOIL and put our like terms together to find out where that y-intercept is. And, that's a possibility. You could do that. And if I did that in this case, I could FOIL. So x times x is x squared. And outside 2, so I have the first outside 2 would be minus 2x. Inside 2, minus 2x. Last 2, minus 2 times minus 2 is plus 4. Then we have the plus 3 off the end. And so when I combine my like terms, it would turn into x squared minus 4x plus 7. And so that actually tells me this y-intercept is going to be up here at 7. So if I wanted to use that point, I could. And then I could reflect that point over the line of symmetry, and there'd be an identical point on the other side. And that would actually give me enough for some good points to graph this parabola. But if I didn't want to go through the trouble of expanding that out and putting it in this standard form, then what I could do is just go ahead and pick numbers below the vertex and above the vertex. So maybe put in 1 and 0 and maybe -1, and then on the other side 3, 4, and 5, and substitute those in. And I could use the table function in my calculator. And some numbers that I could get that would actually fit on this graph, if I plug 0 in, I get 7. If I plug 1 in, I get 4. When I plug 3 in, I get 4 also. And plugging in 4, I get 7. So I can either do that manually or using the table in my calculator. And so then that could give me other points. So if I didn't want to find the y-intercept, these would be alternatives. And actually, I really did find the y-intercept because it's actually right there. But you won't always find that by making a table. So I've also got the 0.14, so this would give me a few more points to work with. There's a point there, oops, in red, and then another point on the other side to get that parabola when I connect it together. And there's a pretty good representation of that function. So what about number 9? So this time my function is x squared minus 4. Well, this is kind of written in vertex form. It's just that there really is nothing being done in terms of a horizontal slide. So this is really the same as saying x minus 0 squared minus 4. And so what that really tells us is that the axis of symmetry is x equals 0. And that my vertex is at 0, -4. So in other words, my axis of symmetry is the same axis of symmetry that I would have for the parent function, which is the y-axis itself. The vertex is actually on that line at -4, so there it is right about here. So in this instance, finding the y-intercept would not be helpful because that already is the y-intercept, it's the vertex. So we could go ahead and put this in the center of our table, substitute in some values that are above and below it, and I usually just will scale by ones and see if that fits in the graph. So substituting a -1, -2, maybe a 1 and a 2. Can use the table function. Again, you could type in x squared minus 4 in your y equals part of your graphing calculator and just use the table from the values from the table, or you could manually substitute each one of these in. So I end up getting a 0 when I plug -2 in, a -3 when I plug -1 in, a -3 when I plug 1 in, and a 0 when I plug 3 in. And again, you can kind of see that, well, you absolutely can see that symmetry that's going on here as you go on either side of the vertex. Since this is the vertex, you see those points repeating on either side. So I'll go ahead and plot those points, and I would have a very good representation of my function. So here at -2, 0, at 1, -3, and 2, 0. And we've talked a little bit about what these points where the parabola crosses the x-axis, those are actually those we call those roots or solutions. We'll talk more about that in upcoming lessons, but just so happened that those happen to be points that I was able to get in my table. So how if they get a little more complicated? Let's take a look at 10 and 11. So on number 10, we've got this negative out in front. So we know what that means. That means this parabola should face down. But other than that, we can still do our same work to find the x of symmetry. So we're going to look at x plus 5. So we know that if we wrote this as a subtraction, like it says in this vertex form, we'd have to write it as x minus -5. And that would tell us then that the x coordinate of the vertex must be -5. Now, another way to look at that is to really just look at what would make this quantity, this x plus 5, equal to 0, and we'd get that same thing, -5. That means our vertex has an x coordinate of -5, and of course the -1 will be my y coordinate. And so I know that this has a x of symmetry right here. And that vertex is at -5, -1. So that'd be right here. Now this is going to face downward. So again, I could, if I wanted to expand out, which this one would be more complicated to expand out because we then have a negative out in front, which makes kind of more layers of complexity there. But we could take that -5, -1 in our table, and we could find some values below it by putting in, say, -6 and -7, and above by putting in -4 and -3. And you can, again, use the graphing calculator table to do that as well. Maybe we could go a little further to -8 and to -2. And here's the values I got from my graphing calculator table. And plotting them looks like I could fit most of these points on here. I could even estimate this -8, -10, -7. I could get the -5, 1, 2, 3, 4, 5. There it is right there. -6 and -2 right there. Got the same points reflected on the other side. And you can see that this parabola does what I would predicted it would have done by looking at the transformation in the equation. I could see that the negative should reflect it down. Check, it did that. The x plus 5 should slide it to the left 5, and yes, it did that. And the -1 should slide it down 1. All those things I can see reflected in my graph. So let's go ahead and designate number 11 as a you-try question. So we'll pause the video, have you give number 11 a try, finding the x of symmetry, the vertex, and completing the table or expanding this out using FOIL to find the y-intercept, or use the table to generate some values that you can put on your graph. So pause the video now. So again, thanks for giving that a try. So you probably picked up right away that this is going to be a vertical stretch. We have the 3 out in front. And so when you have a vertical stretch like that, and the limited space we have on our coordinate plane there, you're not going to fit a whole lot of points because all these points are really 3 times further away than they would normally be on the parent function. And so even though I created a table after finding the vertex at 4, 0, and the x of symmetry being there at x equals 4, really I was only able to fit on a point on either side of that because clearly these points are growing quite large real quickly. So, but that was enough to get a good, pretty decent shape of this parabola and to clearly see that this is much skinnier parabola. This is definitely a vertical stretch. Okay, let's turn the page.